Welcome! My name is Carmen. In this video we will learn what is a detector and how to effectively construct it. A detector is a classifier that describes only one class, assigning every sample to the target class or non-target class. This is an illustration in 1D. The blue dots are data samples from my target class. We need to describe the probability distribution of the class. Let's use, for example, a Gaussian model. Now we can set a threshold on the probability density. Every sample with density above the threshold will be labeled as target, otherwise as non-target. In per class, it is very easy to build a detector. We can do it with one command. The detector PD is trained on the data A. We specify the class the detector will be trained on. For us, there is only one class, called target. Finally, we specify the model, a Gaussian. Note that only models providing probability density or distance can be used to build a detector. By default, the detector set the threshold so that all target samples are accepted. We can choose to be less permissive and, for example, set the threshold to reject 10% of the data using the reject option. Or we can specify how many objects should be rejected. This Gaussian model does not seem the best fit for this data distribution. We can change it, for example, with a parser descriptor. This detector will identify the two data modes. Let's move to the 2D example with the fruit data. We choose banana as our target class. We pass to the detector only the banana class, specifying that the label is banana, and provide the model. The decision boundary will be an ellipse obtained cutting the Gaussian model to the threshold, in such a way that all samples are accepted. This is how the detector boundary would change if I set the threshold to reject 20% of the data. Or this is what happens if I use a parser model. Why do we need to provide the name of the target class? Because sometimes we want to build one class detector for a group of related classes in our problem. For example, we can pass the apple and banana class, which is the first and second in our dataset, and name the target class fruit. If the target name is not found in the list of the classes, all samples are considered target. In this way, we can conveniently make one class detector without any relabeling. If we have examples of the non-target class, we can use them to set the detector threshold. In the fruit data, we have, for example, apples and stones that can help us to find a good threshold for the banana detector. Coming back to our 1D illustration, the dataset B now contains target and also non-target class. The detector always keeps modeling only the target class. We may set some threshold and compute the errors on the target and non-target classes. This will become a point in the error space. We keep changing the threshold and estimate the corresponding class errors. In this way, we construct what is called the ROC characteristic. For our fruit data, this means passing now the complete dataset, specifying the name of the target class, banana, and the model. As the detect will by default split the data into a training set for building the model and the validation set for estimating the ROC. In this way, we construct an unbiased ROC curve. As the detect by default set the operating point on the ROC, minimizing the mean error. We can visualize the ROC and select a different trade-off that better suits our problem. The ROC is stored in the detector pipeline, and the trade-off may be adjusted anytime. The per-class runtime allows us to change it also out of MATLAB, directly in the running application. Summarizing, we have learned what is a detector and how to train it with one command, only with one class, or optimizing the error trade-offs using both target and non-target samples. Thank you for your attention.